Hi, my name is Michael Colef, and I'll be doing problem 2 of homework 5. Okay, so in problem 2, the first part, we're asked to draw the non-zero definition region for little f of x, y. So little f of x, y only exists for x greater than 1, and then the y values are given by this equation over here. So we have did I write this correctly? Yes, I wrote it correctly. Alright, so x equals y. X. So y is in between x and 1 over x. So the line x is just a line like this of slope 1. So at x equals, this should be x, and this should be y. At x equals 1, the line passes through y equals 1. And then the graph of 1 over x is at 1 also it's equal to 1, but at 0 it goes to infinity, and at infinity it approaches 0. So it looks something like this, and it goes eventually to 0. So the y is in between, so it's less than x but greater than this. So the region is here, this shaded area over here. So that answers part 1. Part 2 wants you to find this constant a such that little f of xy is a valid joint density function. So in order, the general definition for a valid joint density function is this, that little f of xy, if we integrate the x from negative infinity to infinity, I'm sorry, this should be dy. If we integrate x from negative infinity to infinity and y from negative infinity to infinity, we should get 1. So now we're going to set that condition for our density function. So we have here 1 over a x squared y. And I'm not going to, I want to wait before I put what I'm going to integrate first. So we want to go from the first integral we want to do is from curve to curve. So we're gonna integrate first y. So we're taking a little small piece over here, right? And we're gonna integrate from here to here first. So that's gonna be the change in y. So that's going to be dy. We're going to integrate first. And since we're integrating from curve to curve, we're going to integrate from this first curve, which is 1 over x, to this next curve, which is just x. Now that we have this piece, so we go from here to here, now we're going to integrate for the x values, which are going to go from 1 to infinity. And this has to be equal to 1. So we need to find this constant. So right now I'm going to move to another page. So let me just write it again so we don't have to keep flipping back and forth. So again, the first integral is from curve to curve, and that's going to be a change in y. And then we do the change in x from 1 to infinity, and this has to equal 1. So we can, anything that doesn't have y we can take out as a constant. I mean, well, 1 over a we can totally take out as a constant because it is a constant. The x part, we can put it in the x integral from 1 to infinity, so it's 1 over x squared here, dx. And all we have now is dy over y from 1 over x to x. So and this has to be equal to 1. This first integral is natural log from x to 1 over x, which is the same thing as writing natural log of x minus natural log of 1 over x, but this is just natural log of x over 1 over x, which is equal to natural log of x squared, which is equal to 2 ln of x. So this is just like an aside. So this first integral is just 2 ln of x. So we get 1 over a, integral from 1 to infinity. We have 2 natural log of x dx over x squared, and this is supposed to equal 1. So we can take the 2 out. So we have 2 over a, 1 to infinity, natural log of x over x squared. I'm also going to move this constant on this side. So I'll multiply by a and then divide by 2. So I'm just going to get rid of this guy, and it's going to be a over 2. So to solve this integral, we do a substitution. So this first substitution, I'm going to call ln of x, I call it w. dw is just going to be 1 over x dx. So as you can see, it takes care of one of the x's in the denominator. But there's another x in the denominator that we have to consider. So if we do the inverse here, we find that x is equal to e to the w. So knowing that, ln of x is w, 1 over x dx is dw, but then we have still an x on the bottom, but that's just going to be e to the w. If I bring it in the numerator, it's e to the minus w. This is still equal to a over 2. Now the limits change. Ln of 1 is 0. Ln of infinity is infinity. Okay. So now we use u substitution. So u, I'm gonna call w u. Du, sorry, that looked like a w. Du equals dw. dv I call e to the minus w. V is minus e to the minus w. So, we'll move to another page. Like this. So, right. So we do UV substitution. So we have UV, so that's going to be W. I'm sorry. Yeah, hold on a second. W. Right, it's going to be W. It's going to be, we have W, and then we have times V, so UV. This is minus e to the minus W, so minus W, I'm just multiplying through, evaluated from 0 to infinity, minus the integral from 0 to infinity of V du. Well, what's V? V is minus e to the minus W, minus comes out, and du is just dw, so we have e to the minus W dw. And this is still supposed to be equal to a over 2. This goes to 0 because the first thing we have infinity, right? But e to the minus infinity goes faster to 0 than w goes to infinity. So the first part of the evaluation is 0, and then e to the minus 0 is 1, but w is 0, so it just gets 0. Now, this guy, we're going to get, is going to be minus e to the minus w evaluated from 0 to infinity, and that's just going to be equal to 1. And that's still equal to a over 2, by the way. So, a just becomes 2. So that is part 2. Now, part 3. Part 3. Now they want us to find the marginal density function. So that's first f of x and then f of y. So f of x is defined as this. We basically integrate out all the y. So, let's see. For every value of x, you want to integrate out the y. So for every point in x, You want to integrate the y out. So this is the general formula, but when we put it for our specific problem, for every point in x, we want to integrate out the y. Well, y goes from 1 over x to x. 1 over x to x. And we just put in our probability density function. So that's going to be 1 over 2x squared y dy. Because we're only integrating with respect to y, we can take out the 1 over 2x squared. We just get 1 over y, the integral of 1 over y is just natural log of, from x to 1 over x. We solved that before. It's going to be ln of x squared, which is just 2 ln of x. 2's cancel, and we are left with ln x over x squared. So this is fx. Now, fy, general formula, is this. But we have to be careful. For every point in y, we have to integrate out x. However, for points y that are underneath 1 or less than 1, by the way, everything is greater. Y is always going to be greater than 0. So we don't care about anything less than 0. But for any points between 0 and 1, any y, we need to integrate out x. But we have to consider only this function. So this function is what? It's y equals 1 over x. But we want to integrate out the x. So we want to go from 1 over y to infinity. And these are only for the points between 0 and 1. So the integral is going to go from 1 over y to infinity. Only for y between 0 and 1. So that's 1 over 2x squared y dx. So what does this become? We can take out the 1 over y, 1 over 2y, we can take out. We're left with this integral, 1 over y to infinity of 1 over x squared. Well, what's that going to become? We still have 1 over 2y. Then we get negative 1 over x evaluated between 1 over y to infinity. At infinity, this guy goes to 0. We have a minus minus, which becomes plus. Then we evaluate at x equals to 1 over y. So 1 over y is just y. So we're left with 1 over 2y times y. So we get 1/2. And just to reiterate, this is between y equals 0 and 1. Now we have to consider the y points greater than 1. For the y points greater than 1, we want to consider, so let's say this point, we want to consider this function. This function is y equals x. So we're going to go from x equals y to infinity. So, okay. So we go from y to infinity of 1 over 2x squared y dx. And this is for y greater than 1. So what does this become? What does this become? This becomes we can take out the 1 over 2y. So we have 1 over 2y integral from y to infinity of dx over x squared. Right. So now we have 1 over 2y negative 1 over x evaluated between y and infinity. So infinity goes to 0, but then we have minus minus, which becomes plus 1 over y. So we're left with 1 over 2y squared. And this is for y greater than 1. Notice, at y equals to 1, this is 1 half. At y equals to 1, it's also 1 half, which is good. So the full answer for f of y is this. 1 half 4. Y between 0 and 1, and then we have 1 over 2y squared for y greater than 1. This is the full answer. Okay, so now we're asked to draw what this looks like. So first I'm going to draw f of x. Where's my f of x? It's here. Ln of x over x squared. So it only exists because x only, this function is only valid for x greater than 1. So we want to go from x, this is by the way fx, we want to go from 1 onward. And this function is going to look something like this. And let's go slowly to 0. How do I know it goes to 0? Well, ln, as x approaches infinity, ln approaches infinity, but it doesn't approach it as fast as x squared approaches infinity. So it's 1 over infinity, which becomes 0. So this approaches 0. And it has some maximum over here. Now, we want to draw f of y. So now we have f of y. And this is y. We start at 1. So, where was I? We have this. So, here, at 1, we have the value 1 half. For y greater than 1, we have a decreasing function like this. Now, between 0 and 1, we have 1 half. And anything before that, we have 0. So this function looks something like this. Now, next part, the last part rather. We want to verify that f of x and f of y are valid density functions. So to do that, we have to make sure that when we take their integral from negative infinity to infinity, that they equal 1. So we have ln x over x squared dx, and we want to check that equals 1. So, now, f of x, because x is only valid greater than or equal to 1, this integral becomes from 1 to infinity ln of x over x squared dx. Now, this is exactly, I'm pretty sure it's the exact same integral that we had. Let me find it. We had it, let's see. We had this integral, the exact integral when solving in part 2 for a. This integral, right? Now, this integral, if we carried it out, followed it here through the substitution, the integral goes to 1. I'll do it again. Actually, I don't have to do it again because it's right here. We go from 1 to infinity. This guy, if we follow the work here, it becomes this. This guy goes to 0, and then we're just left with this, and this guy goes to 1. So we know that this is true. Now, for f of y, I actually have to do it. We haven't done that integral. We have to be careful, though. So from y 0 to 1, we integrate 1/2 dy. And we're adding to that the integral from 1 to infinity, 1 over 2y squared dy. This guy just becomes 1/2, right? This guy becomes 1/2 evaluated, negative 1 over y, evaluated between 1 and infinity. Well, at infinity goes to 0, minus, we get a plus 1. So this guy just goes to 1. So we're left with 1/2 plus 1/2, which equals 1. And that shows that it's a valid density function. And that completes the problem. I just wanted to correct a slight error I made at the end of my solution. If we see here, I put equals in my solution, but little f of x doesn't equal this. I meant to put an arrow to show that the integral of little f of x is supposed to equal 1. And the same thing for y. It's not supposed to be equal. I put like an arrow because I wanted to show that the integral of f of y for wherever it is for the whole thing should be equal to 1.